Today we're going to discuss the Maclaurin and Taylor's polynomials. In the local linear approximation, the tangent line of the graph of a function is used to obtain a linear approximation of the function near the point of tangency. In this discussion, we will consider how one might improve on the accuracy of the local linear approximations by using higher order polynomials as approximating functions. We will also investigate the error associated with such approximation. So to start, let's have local quadratic approximation. Recall from the previous calculus that you have the local linear transformation of the function at x sub 0 can be expressed as you have f of x is approximately equal to f of x sub 0 plus the first derivative of the function x sub 0 times x minus x sub 0. In this formula, the approximating function, you could have the approximating function, the p of x, is equal to f of x sub 0 plus the first derivative, you have x sub 0 times x minus x sub 0. It is a first degree polynomial satisfying the f of you could have the it could satisfy the p sub 0 p of x sub 0 is equal to the f of x sub 0 and the first derivative of p, okay, is equal to the first derivative of the function x of f x sub 0. Thus, the local linear approximation of f at x sub 0 has the property that its value and the value of its first derivative match those of the f of the function at x sub 0. Okay, so as you can see, okay, if the graph of a function f has a pronounced bend at x sub 0, then we can expect that the accuracy of the local transformation or local linear transformation of f at x sub 0 will decrease rapidly as we progress away from the x sub 0. Okay, which is also you can have the illustration of the graph. One way to deal with this problem is to approximate the function f of x sub 0 by a polynomial p of the degree 2 with the property that the value of p and the values of its first derivative match those of the function at x sub 0. This ensures that the graph of the function and the p not only have the same tangent line at x sub 0, but they also bend in the same direction uh, at x sub 0, okay, which both it can be both concave up or concave down. Okay, so as a result, we can expect that the graph of p will remain close to the graph of the function f over the larger interval around the x sub 0 than the graph of the local linear transformation. The polynomial p is called local quadratic approximation of f at x sub 0. So, to illustrate this idea, let us try to find a formula for the local quadratic approximation of a function f at x sub 0. So, this approximation has a form of, okay, you have the f of x, okay, is approximated to the c sub 0 plus c sub 1x, okay, plus c sub 2x squared. Okay, where our c sub 0, c sub 1, and c sub 2 must be chosen so that the values of our p of x, okay, is equal to c sub 0 plus c sub 1x plus c sub 2x squared. Okay, so in this case, okay, the first two derivatives match those of the function f at 0. Thus, we want to have the p sub 0 is equal to f sub 0, f of 0. The first derivative of the function p, or the polynomial p rather, so the first of 0 is equal to the first derivative of the function f of 0, and the second derivative of the polynomial p at 0, okay, would be equal to the second derivative of the function f of 0. But these values of p of 0, the second derivative of p at 0, and the first derivative of p of 0, and the second derivative of p of 0, okay, can be expressed as follows. We could have the p of x, okay, is equal to c sub 0 plus c sub 1x plus c sub 2x squared. And getting the first derivative of p, okay, we could have c sub 1 plus 2c sub 2x. And in this case, our second derivative of p would be equal to 2c sub 2, where in this case, okay, you could have the p of 0 would be equal to c sub 0. Our p of the first derivative of p of 0 is equal to the c sub 1, and the second derivative of our p of 0 would be equal to the 2c sub 2. So it follows the form that our c sub 0 is equal to f of 0. Our c sub 1 would be the first derivative of the function of 0, and our c sub 2 would be equal to the second derivative of f of 0 divided by 2. Okay, so substituting these would yield the formula for the local quadratic approximation of f at x equals 0. So our local quadratic approximation of f at x equals 0 could be, you have the the f of x is approximated to f of 0 plus the first derivative of f of 0 plus the second derivative of f of 0 over 2. This would be x. Okay, since we have a function, and this would be x squared. Okay, so again, our formula for the local quadratic approximation of f at x sub 0 would be f of x is approximated to the f of 0 plus the first derivative of f of 0, x, plus the second derivative of f of 0 over 2 x squared. Okay, so let's have example number 1. Find the local linear and quadratic approximation of e raised to x at x equals 0, and graph x and then graph x e raised to x and the true approximation together. So you have already given the graph. Okay, so first for our solution, we'll let f of x. So for our solution, we let the f of x to be the e raised to x. Then we could have our first derivative of x is equal to the second derivative of f of x, which is equal to e raised to x. Hence, you could have f of x, f of 0 rather, is equal to the first derivative of f, okay, of 0, which is equal to the second derivative of the function f, okay, of 0, which is equal to e raised to 0, which is equal to 1. Okay, thus, okay, the local quadratic approximation of e raised to x at x equals 0 would be, you could have the e raised to x, okay, is approximated to 1 plus x plus x squared over 2. And if this would be our local quadratic approximation of x squared at x equals 0, our linear approximation, okay, which is in this case the linear part of the quadratic approximation. So you have e raised to x, okay, is equal to 1 plus x. Okay, so the graph of e raised to x and the two linear transformation, okay, can be depicted in the graph at the left rather. So as expected, the local quadratic approximation is more accurate than the local linear approximation near x equals 0. Okay. Now let's have the Maclaurin polynomials. It is natural to ask whether one can improve on accuracy of a local quadratic approximation by using a polynomial of degree 3. Specifically, one might look for a polynomial of the degree 3 with the property that its value and the values of its first three derivative match those of the function f at a point. And if this provides an improvement in accuracy, why not go on to the polynomial of even higher degree? So we are led to consider this problem. So you have there the problem, given a function f that can be differentiated n times at x equals x sub 0, find a polynomial p of degree n with the property that as the value of p and the values of its first n derivatives match those of the function f at x sub 0. So we will begin by solving this problem in the case where x sub 0 equals 0. Thus, we want a polynomial that p of x, okay, is equal to c sub 0 plus c sub 1x, okay, plus c sub 2x squared plus c sub 3x cubed plus so on, plus you have c sub n x raised to n. Okay, so for this, okay, we have, okay, f of 0 would be equal to our p of 0. Then our first derivative of f of 0 would be equal to the first derivative of p of 0, and the second derivative of f of 0 would be equal to the second derivative of p of 0, so on up to the the nth derivative of f of 0 would be equal to the nth derivative of p at of 0. Okay, but in this case, okay, you could have our p of x, okay, is equal to this one. Okay, therefore our first derivative would be c sub 1. Okay, it must be c sub 1. You have first c sub 1 plus 2 c sub 2 x plus 3 c sub 3 x squared plus so on, plus you have n c sub n x raised to n minus 1. And in this case, our second derivative of p of x would be equal to uh, 2c sub 2 plus 3 times 2 c sub 3 x squared, no, plus so on, plus you have n times n minus 1 c sub n x raised to n minus 2. Our third derivative of p of x would be equal to 3 times 2 c sub 3 plus so on, plus n times n minus 1 times n minus 2 times c of n x raised to n minus 3. And if we go down, in this case, you could have our p raised the nth derivative of p, okay, of x would be equal to n times n minus 1 times n minus 2 up to 1 c sub n. So to satisfy, okay, we could have our f of 0 is equal to our p of 0, which is our c sub 0, or the constant. And then the first derivative of f of 0 is equal the first derivative of p, okay, of 0 is equal to our c sub 1. Our second derivative of f of 0 is equal to the second derivative of p of 0, which is equal to our c sub 2, 2 c sub 2 rather, okay, which is equal to 2 factorial c sub 2. And our the third derivative of f of 0 is equal to the third derivative of p of 0, which is equal to 3 times 2, okay, c sub 3, which is technically equal to 3 factorial c sub 3. And then the nth derivative of f of 0 would be equal to the nth derivative of p of 0, which is equal to n times n minus 1 times n minus 2 and so on up to 1 times c sub n, which is equal to n factorial c sub n, okay, which yields to the value of our coefficient of p, polynomial p of x, that the coefficients are c of 0 would be equal to f of 0, okay, our c sub 1 would be equal to the first derivative of f, of 0, and then the c sub 2 would be equal to the second derivative of f of 0 over 2 factorial, and then our third coefficient would be the third derivative of f of 0 over 3 factorial, okay, so on, okay, c sub n, okay, would be equal to the nth derivative of f of 0 over n factorial. So the polynomial that results by using these polynomials called uh, nth Maclaurin polynomials for f. Okay, so to define, you have if the function can be differentiated n times at 0, then we define the nth Maclaurin polynomial for f to be the polynomial p of n, p sub n of x is equal to the function, the f of 0 plus the first derivative of x, first derivative of f of 0 x plus the second derivative of function of 0 over 2 factorial x squared plus the third derivative of f of 0 over 3 factorial x cubed plus so on plus the nth derivative of f of 0 over n factorial x raised to n. Note that this polynomial has the property that its value and the values of its first n derivatives match the values of f and its first n derivatives at x equals 0. Okay, so let's have an example. Find the Maclaurin polynomial p of 0, p sub 0, p sub 1, p sub 2, p sub 3, and p sub n for x raised to, for e raised to x rather. So for our solution, in this case, let our f of x to be e raised to x. Thus, our first derivative of f of x would be equal to the second derivative of f of x, which is equal to the third derivative of f of x, which is again equal to so on, okay, the nth derivative of f of x, which is equal to e raised to x. And we could have our f of 0 is equal to the second derivative of f of 0, which is equal to the third derivative of f of 0, which is again equal to the nth derivative of f of 0, which is equal to e raised to 0, which is equal to 1. Therefore, we could have our p of 0, p sub 0 of x is equal to the function, okay, f of 0, which is equal to 1. Our p sub 1 of x would be equal to the f of 0 plus the second derivative, the first derivative of f of 0, okay, x, which is equal to x plus 1. Our third uh, our third polynomial of x. Oh, no, we are still at the second. So the second derivative, the second polynomial of x would be equal to f of 0 plus the first derivative of f of 0 plus you have the second derivative of f of 0 over 2 factorial x squared, which is equal to 1 plus x squared over 2 factorial which is technically equal to 1 plus x plus 1 half of x squared. So our third polynomial of x is equal to, you have f of 0 plus the first derivative of f of 0, x, plus the second derivative of f of 0 over 2 factorial x squared, plus you have the third derivative of f of 0 over 3 factorial x cubed. So this can be formed as 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial, which is equal to 1 plus x plus 1 half of x squared plus 1/6 of x cubed. Therefore, our uh, p sub n of x would be equal to f of 0 plus the first derivative of f of 0, x, okay, plus the second derivative of f of 0 over 2 factorial plus the third derivative of f of 0 over 3 factorial plus so on, plus the nth derivative of 0 f of 0 over n factorial x raised to n. This must be x squared x cubed. Okay, so which is equal to 1 plus x plus x squared over 2 factorial plus so on, plus x raised to n over n factorial. Or this can be also be written as 1 plus x plus, you have 1 half of x squared plus so on, plus you have 1 over n factorial of x raised to n. So if we are going to graph this one, okay, this shows that the graph of e raised to x, which is the one in the blue, and the graph of the first four Maclaurin polynomials. Note that the graph of the first polynomial x, the second polynomial x, and the third polynomial x are virtually indistinguishable from the graph of e raised to x near x equals 0. So these polynomials are good approximations of e raised to x for x near 0. However, the farther x from the 0, the poorer the approximation become. This is typical of the Maclaurin polynomial for a function f of x. They provide good approximations of the f of x near 0, but the accuracy diminishes as x progresses away from 0. It is usually the case that the higher the degree of polynomial, the larger the interval on which it provides a specified accuracy. So accuracy issues will be investigated later. Okay. So let's have the example number 3. Find the nth Maclaurin polynomials for sine x. So in this case, the Maclaurin polynomials for sine x, only the odd powers of x appears explicitly. So to see this, let's have our f of x is equal to sine x. Then the first derivative of x is equal to cosine x. Now this is our if we are going to substitute the f of 0, this is equal to 0. And then if this would be substituted by 0 again, this is equal to 1. Okay, the second derivative of x is equal to negative sine x. Now if we are going to substitute this one by 0, this is equal to 0. Then the third derivative of f of x is equal to negative cosine x. Then you have the third derivative of f of 0 would be equal to negative 1. Okay, in this case, since the the fourth derivative of x is equal to sine x, which is equal to the f of x. So the pattern 0, 1, 0, negative 1 will repeat as we evaluate successive derivatives at 0. Therefore, the successive Maclaurin polynomials for sine x would be, you could have um, uh, um, you have uh, p of 0 is equal to our wrong. It should be the p sub 0. Okay, p sub 0 x is equal to 0. Our p sub 1 of x would be equal to 0 plus x. Our p sub 2 of x is equal to 0 plus x plus 0. Our p sub 3 of x would be equal to 0 plus x plus 0 minus x cubed over 3 factorial. So our p sub 4 of x would be equal to 0 plus x plus 0 minus x cubed over 3 factorial plus 0. Then our p sub 5 of x is equal to 0 plus x plus 0 minus x cubed over 3 factorial plus 0 plus x to the fifth over 5 factorial. And our p sub 6 of x is equal to 0 plus x plus 0 minus x cubed over 3 factorial plus 0 plus x raised to 5 over 5 factorial plus 0. And our p uh, of p sub 7 of x would be equal to 0 plus x plus 0 minus x cubed over 3 factorial. This must be tama. Okay, plus 0 plus x to the fifth over 5 factorial plus 0 minus x to the 7th over 7 factorial. Okay, because the 0 terms, each even order Maclaurin polynomial after the p sub 0 x is the same as the succeeding odd order Maclaurin polynomial. That is, you could have, okay, you have p sub 2k plus 1 of x, okay, would be equal to p sub 2k plus 2x which is equal to, you have x minus x cubed over 3 factorial plus uh, x raised to 5 over 5 factorial minus uh, you have x raised to 7 over 7 factorial plus so on plus you have negative 1 raised to k. You have x raised to 2k plus 1 over the quantity 2k plus 1 factorial, where our k would be equal to 0, 1, 2, and so on. Okay. So if we are going to graph this one, this would be the graph. Okay. So our sine x, you have there the sine x, then you have the polynomial, the first polynomial of x, a p sub 1x, you have p sub 3x, p sub 5x, and p sub 7x. Okay. So let's have another example. Find the Maclaurin polynomials for cosine x. In the Maclaurin polynomials for the cosine x, only the even power of x appears explicitly. So the computation are similar to our previous computation. Okay, so we have our p sub 0 of x is equal to p sub 1 of x, which is equal to 1. And then our p sub 1, p sub 2, because even, okay, p sub 2 of x is equal to our p sub 3 of x, which is equal to 1 minus x squared over 2 factorial. Our p sub 3, p sub 4, p sub 4, k of x is equal to p sub 5 of x, which is equal to 1 minus x squared over 2 factorial plus x raised to 4 over 4 factorial. Then our p sub 6 of x would be equal to p sub 7 of x, which is equal to 1 minus x squared over 2 factorial plus x raised to 4 over 4 factorial minus x raised to 6 over 6 factorial. So in general, okay, if we are going to, okay, if we are going to get the Maclaurin polynomials for cosine x, okay, out from what we have in the previous slide, you have the p of 2k, p sub 2k, okay, of x is equal to p sub 2k plus 1 of x, which is equal to 1 minus x squared over 2 factorial plus x raised to 4 over 4 factorial minus x raised to 6 over 6 factorial plus so on, plus you have the negative quantity negative 1 raised to k, x raised to 2k over the quantity 2k factorial, where our k is equal to 0, 1, 2, and so on. Okay, so if we are going to graph that one, okay, this shows our cosine x, our p sub 0 x, our p sub 2 sub p sub 2 of x, p sub 4 uh, of x, and p sub 6 of x. Okay, so let's have a Taylor polynomial. So up to now, we have focused on approximating a function f in the vicinity of x equals 0. Now we will consider the more general case of approximating f in the vicinity of an arbitrary domain value x sub 0. The basic idea is the same as before. We want to find the nth degree polynomial p with the property that its value and the values of its first and derivatives match those of f or the function at x sub 0. However, rather than expressing p of x in the powers of x, we will simplify the computation if we express it in powers of x minus x sub 0. So that is, you could have, uh, so you could have, um, let's go to the definition. So if f can be differentiated n times at x sub 0, then we define the nth Taylor polynomials for x about x equals x sub 0 to be p sub n of x is equal to f of x sub 0 plus the first derivative of x sub 0 minus the quantity x minus x sub 0 plus the second derivative of x sub 0 over 2 factorial the quantity x minus x sub 0 squared plus the third derivative of f of x sub 0 over 3 factorial times the quantity x minus x sub 0 cube plus so on plus the nth derivative of f of x sub 0 over n factorial times the quantity x minus x sub 0 raised to n. Okay, so in this case, when we are going to substitute, okay, um, our uh, our c sub 0, okay, in this case, uh, our c sub 0 would be equal to f of x sub 0. Our c sub 1 would be equal to the first derivative of x sub 0, okay, and then c sub 2 will be equal to the second derivative of f of 0 over 2 factorial, and then our c sub 3 would be equal to the third derivative of f of x sub 0 over 3 factorial, so on up to our c sub n would be equal to the nth derivative of f of 0 over n factorial. Okay, so let's have an example. Okay, find the first four Taylor polynomials for the natural logarithm x about x equals 2. So in this case, okay, to answer this, let, okay, our f of x would be equal to the natural logarithm of x. Thus, in this case, our f of x would be equal to the natural logarithm of x. Now, if we are going to substitute that one by 2, then you have the natural logarithm of 2. Now, the first derivative of x would be equal to the first derivative of natural logarithm of x would be 1 over x. Then substitute it by 2 rather. That would be equal to 1/2. Then the second derivative rather, of x would be equal to, in this case, you have negative 1 over x squared. So f of, this is first derivative, this is the second derivative of 2 would be equal to negative 1/4. And then the third derivative of f of x would be equal to 2 over x cubed, which is equal to the third derivative of x, of 2, which is equal to 2 over uh, 4 2 raised to 3, which is equal to 1/4. Okay. So in this case, you have our p sub 0, our polynomial sub 0 of x would be equal to the f of 2, which is equal to the natural logarithm of 2. Our p sub 1 is of x would be equal to uh, f of 2 plus the first derivative of 2 times x minus 2, which is equal to the natural logarithm of 2 plus 1/2 of x minus 2. And then our p sub 2 of x would be equal to f of 2 plus the first derivative of f of 2 times x minus 2 plus the second derivative of f of 2 over 2 factorial times x minus 2 quantity squared, which is equal to the natural logarithm of 2 plus 1/2 of x minus 2 minus 1/8 of the quantity x minus 2 squared. And then our p sub 3 of x would be equal to, you have f of 2 plus the first derivative of 2 times the quantity x minus 2 plus the second derivative of f of 2 over 2 factorial times the squared quantity of x minus 2 plus you have the third derivative of f of 2 over 3 factorial times the cube quantity of x minus 2. So which is equal to the natural logarithm of 2 plus 1/2 of the quantity x minus 2 minus 1/8 of the squared quantity of x minus 2 plus you have 1 over 24 of the cube quantity of x minus 2. Okay, so let's have the sigma notation for Taylor and Maclaurin polynomials. So frequently, we want to express the previous formula in the sigma notation. To do this, we use the notation f raised to the kth derivative of f at x equals x sub 0. And we make the convention that you have the f raised to not raised, that the zeroth derivative of f of x sub 0 denotes that f of x sub 0. This enables us to write the summation of you have the kth derivative of f of x sub 0 over k factorial times the uh, the quantity x minus x sub 0 raised to k from 0 to n is equal to the f of x sub 0 plus the first derivative of x sub 0 times x minus x sub 0 plus the second derivative of x sub 0 over 2 factorial times the squared quantity of x minus x sub 0 plus so on plus the nth derivative of x sub 0 over n factorial times the quantity x minus x sub 0 raised to the power of n. So in particular, we can write the nth Maclaurin polynomial for x as the summation of the kth the kth derivative of f of 0 over k factorial times k raised to k from 0 to n is equal to f sub 0 plus the first derivative of f of 0 x plus the second derivative of f of 0 over 2 factorial plus times x squared plus so on plus the nth derivative of f of 0 over n factorial times x raised to n. Okay, so let's have this example. Find the nth. Okay, so find the nth Maclaurin polynomials as expressed in the sigma notation. So you have 1 over 1 minus x. So in this case, okay, we have f of x is equal to 1 over 1 minus x. So our uh, f of x would be equal to 1 over 1 minus x, which if we are going to substitute it by 0, which is equal to 1, which is technically 0 factorial. So our first derivative of f of x would be equal to 1 over the squared quantity of x minus 1 minus x, which is if we are going to substitute it with 0, this is equal to 1, which is 1 factorial. Then the second derivative of f of x is equal to 2 over the cube quantity of 1 minus x. Substitute of 0 is equal to 2 or 2 factorial. And then the third derivative of f of x is equal to 3 times 2 over 1 minus 4 1 minus x raised to the power of 4, which is equal to 0 is equal to, in this case, you have 3 factorial. Then you have f raised the fourth derivative of f of x is equal to, you have 4 times 3 times 2 over, you have the quantity 1 over x raised to 5, which is, you have the fourth derivative of f of 0 is equal to 4 factorial up to, okay, so you have the kth derivative of f of x is equal to k factorial over, you have 1 minus x quantity raised to k plus 1, which is, you have the the kth derivative of f of x is equal to k factorial. So in this case, substituting the the kth derivative of f of 0 is equal to k factorial. Okay, this yields the nth Maclaurin polynomial for 1 over 1 minus x would be, so our answer, you have the p sub n of x is equal to the summation of x raised to k from 0 to n is equal to 1 plus x squared plus so on plus x raised to n, where our n would be equal to 0, 1, 2, and so on. So that is our answer. Okay, find the nth Taylor polynomial for for 1 over x. Okay, about x equals 1, and express it in sigma notation. So in this case, we are going to have our f of x to be 1 over x. Okay. So similar, you have the computation similar to the previous example. So we have, okay, to shortcut, you have f of 1 is equal to 1, f of the first derivative of f of 1 is equal to negative 1. The second derivative of f of 1 is equal to 2 factorial rather. Then the third derivative of f of 1 is equal to negative 3 factorial. And then the fourth derivative of f of 1 is equal to 4 factorial, and so on. You have the kth derivative of f of 1 would be equal to the quantity negative 1 raised to k factorial. So substituting our kth derivative of f of 1, which is the quantity negative 1 raised to k factorial. Okay, so with x sub 0 equals 1, this yields our nth Taylor polynomial for 1 over x to be the summation of the quantity negative 1 raised to k times x minus 1 raised to k from 0 to n to be 1 minus quantity x minus 1 plus the quantity x minus 1 squared minus, you have x minus 1 quantity cube plus so on, plus you have the quantity negative 1 raised to n times the quantity x minus 1 raised to n. Okay. So let's have the nth remainder. So it will be convenient to have a notion or notation for the error of approximation f of x approximated to the p of p sub n of x. Accordingly, we will let the the r sub n of x denoted the difference between the f of x and its nth Taylor polynomial. So that is our r sub n of x is equal to the f of x minus the p sub n of x, which is equal to the f of x minus the summation of the kth derivative of f of x sub 0 over k factorial times the quantity x minus x sub 0 um, raised to the power of k from 0 to n. This can be also be written as f of x is equal to the p sub n of x plus, you have r sub n uh, of x is equal to the summation of the k derivative of f of x sub 0 over k factorial times the quantity x minus x sub 0 raised to k from 0 to n, plus you have r sub n of x. So this r sub n of x is called the nth remainder of the Taylor series of f, and uh, the second formula. Okay, so this would be the nth remainder, and this one, okay, is called Taylor's formula with remainder. Okay, so finding a bound for the nth remainder of the Taylor series gives an indication of the accuracy of the approximation uh, p sub n of x, which is approximate to the f of x. Okay, so let's have the theorem. Okay, if the function f can be differentiated n plus 1 times on an interval containing the number x sub 0, and if m is the upper bound for the absolute value of the uh, n, n plus 1 derivative of f of x on the interval, that is the absolute value of the n plus 1 derivative of f of x is less than or equal to m for all x in the interval, then the absolute value of the remainder of the nth remainder of the Taylor series of f, okay, uh, is less than or equal to m over the quantity n plus 1 factorial times the absolute value of x minus x sub 0 raised to x plus 1 for all x in the interval. Okay, so let's have example number 7. Use the nth Maclaurin polynomial for e raised to x to approximate e to 5 decimal place accuracy. So for our solution, we note first that the exponential function e raised to x has a derivatives of all orders of every real number x. So from the previous examples, which is example number 2 that we have, the nth Maclaurin polynomial for e raised to x is you have the summation of x raised to k over k factorial from 0 to n, which is equal to 1 plus x squared over 2 factorial, plus so on, plus x raised to n over n factorial. In this, we have e is equal to e raised to 1, which is approximate equal to the summation of 1 raised to k over k factorial from 0 to n, which is equal to 1 plus 1 plus 1 over 2 factorial plus so on plus 1 over n factorial. Thus, our problem is to determine how many terms to include in the Maclaurin polynomials for e raised to x to achieve 5 decimal place accuracy. That is, we want to choose n so that the absolute value of the nth remainder at x equals 1 satisfies. So you have the absolute value of the remainder, okay, in of 1 is less than or equal to 0.000005. Okay, so that, so determine n Okay, we use the remainder estimation theorem with f of x equals e raised to x, where x is equal to 1 and x sub 0 is equal to 0 in the interval 0 1. So let's take note of that one. So we are going to use the theorem with f of x would be equal to e raised to x, then our x would be 1, our x sub 0 is equal to 0 at the interval 0 1. So in this case, we can now follow that our absolute value of the remainder of 1 is less than or equal to m over the quantity n plus 1 factorial times the absolute value of 1 minus 0, okay, and raised to n plus 1, which is technically equal to m over the quantity n plus 1 factorial, where m is an upper bound on the value of f raised to not raised f the n plus 1 derivative of f of x, which is equal to our e raised to x for x in the interval 0 1. However, the e raised to x is an increasing function, so its maximum value on the interval 0 1 occurs at x equals 1. That is, we have e raised to x is less than or equal to e on this interval. Thus, we make that our m is equal to e. So, in this case, we could have uh, the absolute value of the remainder of 1 is less than or equal to e over the quantity n plus 1 factorial. Unfortunately, this inequality is not very useful because it involves e, which is which is the very quantity we are trying to approximate. However, if we accept that e is less than 3, then we can replace this with the following less precise but more easily applied inequality. Take note that we know that e is less than 3. So in this case, if e is less than 3, then we have the remainder, okay, absolute value of remainder is less than 3 over the quantity n plus 1 factorial. Thus, we can achieve the 5 decimal place accuracy by choosing n so that we have you have 3 over the quantity n plus 1 factorial would be less than or equal to 0.0000005, or you have the quantity n plus 1 factorial would be greater than or equal to 600,000. Since 9 factorial is using calculator, okay, using calculator, our 9 factorial would be equal to 362,880, and our 10 factorial using calculator, you could have 3,628,800. The smallest value of n that meets this criterion is n equals 9. Thus, the 5 decimal place accuracy of e, okay, so our e would be equal to approximately equal to 1 plus 1 plus, okay, you have 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial plus 1 over 7 factorial plus 1 over 8 factorial plus 1 over 9 factorial, which is equivalent which is approximately equal to 2.7128. So you can check you can check using your calculator with the 12 digit representation of E, which is equal to E uh 2.7182818286, which agrees with the preceding approximation when we rounded to the 5 decimal places. Okay, let's have this example. Use the remainder estimation theorem to find the interval containing x equals 0 throughout which f of x is equal to cosine x can be approximated by the p of x equals 1 minus the quantity x squared over 2 factorial to 3 decimal place accuracy. So for our solution, we note first that our f of x, take note, our f of x, okay, is equal to cosine x, has a derivatives of all orders for every real number x, so that the first hypothesis of the remainder estimation theorem is satisfied over any interval that we choose. The given polynomial p of x is both second and third Maclaurin polynomials for cosine x. So we will choose the degree n of the polynomial to be as large as possible, so that we'll take n equals 3. So our problem is to determine an interval on which the absolute value of the third remainder at x satisfies the remainder of the third r over r sub 3, okay, of x would be less than or equal to 0.0005. So we will use the remainder theorem, remainder estimation theorem, with f of x equals cosine x, and our n would be 3 at x of 0 is equal to 0. So in this case, you have this one, 3 of x, okay, is less than or equal to m over the quantity 3 plus 1 factorial, okay, of the absolute value of x minus 0, absolute value, okay, raised to 3 plus 1, which is equal to the m of the absolute value of x raised to 4 over 24. Okay, so where m is the upper bound for the fourth derivative of x, which is equal to the absolute value of cosine x. So the absolute value of cosine x is less than or equal to 1 for any real number x. So in this case, we can make that our m to be equal to 1. So in this case, if m is equal to 1, then our the absolute value of the remainder, okay, is equal to not equal, this must be less than or equal to the absolute value of x raised to 4 over 24. Thus, we can now achieve the 3 decimal place accuracy by choosing the values of x for which our absolute value of x raised to 4 over 24 must be less than or equal to 0.0005. Or we could have that the absolute value of x must be less than or equal to 0.3309. So the interval, in this case, the interval would be you have um, from negative 0.3309 to positive 0.3309. Okay, is one option. Okay, so we can check this answer. Okay, you could have the graph of the f of the absolute value of f of x minus p of x over the interval negative 0.3309 0.3309. Okay, so that ends our presentation today.